Hello again, it's your friendly heavy physics teacher here with a lesson for my Regents Physics class, Unit 10, Lesson 3, Electromagnetic Applications. And in this lesson, we are going to explore how electromagnetic induction affects a current carrying wire or a stream of charged particles as they move through or are affected by an external magnetic field. So we're going to be looking at what is the principle behind electric motors and what is the magnetic effect on a stream of charged particles moving through a space. Okay, let's imagine that we have a wire and it's in between two magnetic poles. Okay, so here's a south magnetic pole, here is a north magnetic pole. This could be two ends of a U-shaped bar magnet where the U is going into the board here and coming out over here. It creates a magnetic field from the north pole to the south pole that's going to go across this wire and affect this wire. This is our top view. We're looking down on the wire. All right, the current we know is flowing that way. If we look at it from the side, in other words, if we were to lie on the floor and look up at the board, this is the view we would see, the side view over here. All right, so let me start by looking at the side view here. Okay, now if I apply my first right-hand rule to determining what is the magnetic field around this wire, can you see that it would be rotating in a counterclockwise fashion? Now, the field isn't actually rotating. The field is not itself moving, but it has that counterclockwise orientation to the direction of the magnetic field. Just so that you can see it, thumb would be pointing out of the board, okay? And my fingers, notice how they wrap around that. All right, so I'm going to draw with a different color the magnetic field of the wire. The green here is the magnetic field of the external magnets. I know that's a little disconcerting that a moment ago there was nothing and now blink, there's something there, okay? All right, but here's the blue here represents the magnetic field of the wire, okay? Now, notice that where the blue crosses perpendicular to the green magnetic field, nothing's going on there. But notice on bottom, okay, we've got the blue magnetic field going in one way, the green magnetic field going in the other way. Well, remember that if you have two opposite fields, what are they going to do to each other? Okay, the thought is that they're canceling. But that cancellation, quote unquote, cancellation, is actually creating an attraction in here. All right. It's pulling everything together in this direction. Notice that on top, the direction of the blue and the direction of the green are in the same direction. If you have two magnetic fields that are in the same direction, then that creates a repulsion. So physically, there's no forces happening side to side, so the wire can't go side to side. But physically, it's attracted on bottom, repelled on top. And that means that in real, actual terms, mechanical terms, this wire is being pushed that way. It's got an interaction that is creating a change in motion. The force is causing it to go downward. And so we call that the magnetic force acting on the wire by the external magnetic field. Notice that over here, if you translate it to the different view, okay, on top of the wire, it's in the same direction. On the bottom of the wire, below it, or if we were to go behind the board here, it would be in the opposite direction to this B field. Again, the top is repelling, the bottom is attracting. So in this diagram, we would say it's going into the board or into the page. Okay? Two versions of the same thing that's happening here. All right? So, in order to have an easy way of figuring out which way the magnetic force is acting on the wire to move the wire, we're going to use what we call the third right-hand rule. Okay, here we go. Third right-hand rule. If you put your right hand up, all right, just like so, see how I sort of got a similar diagram to what's there, okay? So we have three vectors, and they're going to be mutually perpendicular to each other, okay? Your fingers are going to represent the magnetic flux lines of the external field that's going to be affecting the wire. Your thumb, if you do this with your hand, your thumb, all right, is going to be perpendicular to your fingers when you stick it out like so. Okay? Your palm is going to represent the force that the magnetic field is exerting on the current carrying wire. So this is the force and the magnetic field that that's causing it interacting with the magnetic field of the current carrying wire. All right? So we're using the FBI rule to figure out, see, FBI, to investigate how electromagnetism is happening. Yes, pun very much intended, of course. All right? So let me go back to that diagram and show you how to use the third right-hand rule with that diagram. Okay, here we go. All right? If I look at this, the magnetic field is going from north to south. So I'd have to put my hand, oh, this is really awkward. I'm going to turn this over. Okay? Haha. So it's not so awkward anymore. Okay? So over here, the magnetic field is going from north to south. So my fingers point from north to south. See? There's the flux lines. Oh, look at my thumb. My thumb is in the direction of I in the wire. Which way is my palm pressing on that wire? It's pressing down into the page. Now, didn't we say that a moment ago, that that's the way the force would be acting based on this diagram? Okay, here we are with this one. Okay, my fingers are the magnetic flux lines. Put them in the direction of the magnetic field, so from north to south. Oh, the current is coming out of the page in this diagram. So that means my thumb has to be pointing out of the page. Notice which way is my palm pressing on the wire. Boom, it's pressing this way. Okay, and so for this diagram, we would mark on here force acting that way. Yes, I've turned the board upside down, so we have to realize that reorientation. Okay? Now, this has implications for electric motors. Just a moment. Alrighty, this is a very simplified look at what the essence of an electric motor is. Okay? The essence of an electric motor is you've got an external field magnet with a wire loop, at least one wire loop, that is on an axle of some sort so that it can rotate. And in this case, the rotation would be into and out of the board here. This is the side view of it. Okay? This could either rotate clockwise or, counterclockwise or clockwise in this diagram. So this is the side view, this is the top view, okay? So using our third right-hand rule, all right, notice that if I put my hand next to here, I have to direct my fingers this way across it, all right? Current on this side is up, so the force acting on this wire is up out of the page on this side of the wire. But the current flows. Now notice when the current is flowing parallel to the magnetic field, there's actually no effect. The magnetism of the wire isn't interacting with the magnetism of the external field. Okay, so any current that is acting parallel to the magnetic field doesn't cause a force. Go over here, and now notice that if I were to put my hand in there, okay, yeah, don't look at my armpit, sorry. The force is acting into the page here. So it's acting up here, it's acting down there. So this is going to cause it to rotate. Problem arises that if we keep this direction of current flow, going to pop over here and it's going to push it back. So you'll get this vibrating back and forth. So we have to figure out a way mechanically or electrically of switching the wire, switching the direction of current in the wire every half turn. All right? And there are ways of doing that. Please refer to the supplemental worksheet that I sent home, supplemental information packet on the parts of an electric motor, and look at the commutator and slip rings that would be down on this part of our diagram. That's how they switch the current so that this can continue to rotate through the field. Okay, now let's look at it over here. All right, we've got our magnetic field, okay, going from the north. I'm sorry, that looks like an X. It's supposed to be an N. From the north to the south. Okay, and if we look at our fingers, now this is my left hand, remember. If my fingers are pointing in that direction, okay, and the magnetic field, the current is coming out, notice when my palm pushes down here, over here, it would push up. So we get this rotation going on here. Switch the current halfway through the rotation, and it keeps that orientation happening. All right, so that this is continuously flipping around. This is the principle on which an electric motor works. Okay, what do you think will happen if instead of just one loop, I do 2, 3, 4, 5, 100, 1,000 loops of wire here? I wouldn't have to change the amount of current, would I? But each new loop adds to the magnetic effect. So it adds to the force. And so you can create a stronger electric motor, a more powerful electric motor, by having a lot of loops of wire on this part here. This part of an electric motor is known as the armature. This right over here is the armature. Okay? And very often in a motor, you'll see the armature look like this. Okay? Here's an electric motor. All right? And you'll notice that the central core of it, right here, that's an electromagnet. Okay? And so, according to the way I drew those pictures, this is the first orientation. All right? You can see how the loops of wire are like this around that central core. Yeah, okay. So my magnetic poles here, all right, my magnetic poles here seem to be pretty far away. All right, but notice that when you rotate this down, okay, this creates an electromagnet that now in this orientation can strongly interact with these poles. So if this were a north pole over here and this were a north pole here, if this were rotating toward it, caused by the effect here, the first part pushed it down, and now north and north, that's going to create a repulsion that continues the move. South and south continues the repulsion. All right. So for a moment, this becomes attracted over here, and then down here on this part, on the bottom part, right here, notice that right here, right there, there's a split. You see that line across? That's the split in what we call the commutator. Notice that as I rotate this halfway, the top half is going to move in contact with this down here. The bottom half is moving in contact with this one up here. So now I get, this is what physically switches the direction of the current over here in the armature. Okay? And so that's what gets this to go around when you have electricity going in it in a particular way. All right? So that's the basic kind of electric motor you can have. All right? Now, the other way to do this is you don't have one of these commutators at all. You just have a couple of slip rings that these rub against. These are called brushes. And when these rub against the slip rings and you input changing current in here, in other words, alternating current, that naturally is going to flip the direction of the current in here. And it'll flip it so that it will only rotate according to that flip. And so whatever is the rate of change of current coming into your motor, that's going to create the rate of change of current in the armature, which is going to create the spin. The amount of force that's generated is dependent on the amount of current, not its direction, but it's an amount of current. All right? So the electric motor equation is this. Okay, here's your equation for the electric motor, okay? The force on the wire segment that's being acted on by the field. First off, any wire segment, part of the loop of the wire that is not perpendicular to the field, doesn't have a force acting on it, okay? So the force acting on the wire is equal to the magnetic field intensity times the amount of current flowing in the wire times the length of the wire that is being affected by the field when the field and the wire are perpendicular to each other. Okay? So F equals BIL. Force on the wire equals the magnetic field intensity times the current flowing in the wire times the length of the wire affected by the part of the magnetic field it's in. Remember, the current in that length of the wire, this term here, must be perpendicular to B for this to happen. There's an additional trig thing that I could add on here for, what is the component of the interaction between here. We're not going to worry about that. We're only going to worry about when is the maximum force exerted. It's when the B and the I are perpendicular to each other. Okay? Some other applications of this principle. Okay, here we have a representation of an audio speaker. Now, at the back of the audio speaker is this thing which, if you cut it in half, would look like an E, because that's what it looks like from its face, from the front view. Okay, so if you stand looking at a speaker and you were to pull everything apart, the back part of it would look like this kind of a cup, metal cup, where the outer ring would be one pole, the central core, the central knob in it would be the other pole of the magnet. All right, think of it as a bunch of U's all the way around in a circle. All right, so here, this is circular here. All right, except we've cut it in half to give us the cross section. Now, on this is placed a cone that has a flexible binding so that the cone is able to be able to move a little bit in and out. All right. And then at the base of the cone, around a cylinder wrapped that's attached to the bottom of the cone, we have a coil of wire wrapped around that. All right. Now notice that this coil of wire can have electricity sent into it. All right. And when the electricity comes in one direction, in one particular way, let's say that the current direction is such that on top here it's going into the field. On the bottom here, it's coming out of the field. All right. So if this is the North Pole and the central core is the South Pole, here's what's going on. Third right-hand rule. Magnetic field is down toward the center here from the top. Okay. The current is into the board. Notice that I would have to push my thumb into the board here. And notice which way is my palm acting? It's acting to push the cone this way. Now, immediately flip the current. All right. If I flip the current, notice that my palm has to go out. All right. I didn't flip the current though, did I? I flipped my fingers. That's a magnetic field. That stayed this way. So here, flip my current. When I flip my current, aha, my thumb is what needs to switch. Flip my current, flip my current, flip my current. Push, 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 push. Do you see that by flipping the current, it would create a vibrational situation here? If the current is switched at the same rate as which a sound is made, it would make a sound. This would be pushing the air in and out, creating pressure waves that go out from it. Okay? And so that's how an audio speaker works. All right? So here we are using the third right-hand rule in order to be able to hear each other. Okay? Final thing, what would happen if instead of a coil of wire, instead of just a wire, I had a stream of charged particles moving through space? Okay, what do you mean stream of charged particles, Mr. Welkley? Well, how about alpha particles? Alpha decay happens naturally, and you can create a situation where you get all the alpha particles decaying off of some particular material to move in one direction. Okay, so here's my stream of alpha particles coming out. If I want to deflect that stream away from its straight line path, all I have to do is have them move through a magnetic field that is perpendicular to that motion. Okay? And so notice with this, alpha particles are positively charged, so that's the same direction as current. Magnetic field is into the board here. Notice that which way is my thumb acting right there, or which way is my palm acting right there? It's going to create a force that's perpendicular to the motion of the particles. Oh, if a force is perpendicular to the motion of the particles, we call it what kind of force? Centripetal force. So the magnetic force here is equivalent to a centripetal force. And that's what causes the path to curve. You make this big enough, and you actually can cause the particles to begin circling on themselves. Can anybody say Large Hadron Collider and the big circle that it makes? They use magnetic fields in order to cause that stream of protons that they're using, the stream of protons, to bend around that massive, massive circle. Okay? And they're using electromagnets periodically placed around it to maintain that bending that creates the circle all the way around. Okay? So there you have it. How we can use the third right-hand rule to figure out how the magnetic field, the external magnetic field, is acting on the charged particles which themselves, because they're moving, create their own magnetism. So in a wire, the magnetic field of the wire interacts with the external magnetic field and causes it to attract or repel in a particular direction. Third right-hand rule allows us to figure out which way that interaction is happening. Direction of flow of positive charge, current. Direction of the external magnetic flux lines, the field lines, B. Palm. Out of the palm is the way the force acts. So think of this as how you would press on something. Okay? Thank you very much. This is your friendly heavy physics teacher signing off for this particular lesson. We'll see you during the review session in a day or two. And please check your emails for other information about how we're moving forward. Have a great one, folks. Bye-bye.